Okay, so in the last lecture, we created our first strategy, right? We're looking to, okay, let me just correct some errors first. I mean, some minor errors. First of all, I think I wanted to put negative infinity here. And also, this is high minus low, so this should be low, right? We want to go ahead and implement our second strategy. So let's just go and copy the whole alpha class over again, right? So let's copy, and then go here, again, put alpha 2, copy this, put it over here. So we're going to do this, right? Okay. And we want to compute our second strategy. So this was over here. Let's copy that over. And like before, we want to implement our strategy. But this one is considerably easier. We're going to do something a little bit different in terms of the position sizing. So later we will discuss that. So alpha equals to negative 1 multiplied by 1 over, okay, that's NCF equals to self dot df NCF. This is 1 minus NCF dot open NCF dot close. So that would be 1 minus open and close. And then we're taking the negative of that. And then we're taking the rolling 12 mean. So okay, rolling 12 dot mean. So that will be our alpha. We can then say put that over here, right? Say this is the alpha. So in this case, there is no cross-sectional computation. Everything is a time series. So we can put this, and let's say we want to do a forward fill. Dot fill NA, that equals to forward fill. Sample eligible. Okay, we want to have one more operation. So we want to have something like, as we did in the previous class. We want to make sure that the alpha value is non-null. So that's good. And this is our alpha computation, fairly simple. But we're going to do something a little bit different in terms of position sizing. So let me compute the alpha scores. In the previous alpha, what we did was compute the alpha scores, then create and sort it, and go along the top 25 percentile basket and short the bottom 25 percentile basket. But in this particular scenario, right, we want to have a score. So we want this to be the raw signal value. Okay. So this is open over close. So this is going to be either greater than 1 or negative 1 or lesser than 1. So this can be either positive or negative. And this also can be either positive or negative. So the mean value over the 12-day period can be positive or negative. And we're just going to treat this as the raw forecast value. So we're going to take same thing we did here, right? We're going to take this, but instead of doing a long short basket, instead of doing a long short basket, we're going to use this as the raw forecast. So we're not going to do any sorting or creating of baskets. In this scenario, we can even treat every single instrument. But then we will have to consider the position sizing, right? So to demonstrate that, let me just print this out, and let's try to run that inside the main file. So from alpha 2, import alpha 2, and let's say we're going to run alpha 2 now. So let's try to run this particular function and see what we arrive at. So we'll compute the alpha scores, but inside the previous one, we could divide equally among the open positions, right? In this scenario, we're not having any open long or short baskets. So this is going to be slightly different. So let's go ahead and see our alpha scores. Now you can go ahead and see this dictionary, right? So some of them will be positive and some of them will be negative, but they're all very small values. But in terms of the magnitude, they're also quite different from one another. So let me just show this here by writing, right? So we're going to have. Okay, so as you can see, the voice recording is a little bit problematic. So I'm just going to voice over this one and try to explain this as we go along here. So this is suppose we have different forecasts for Apple and Meta, right? And we have say five. Our forecast is 5 for Apple and -1 for Meta. Then this is the degree of confidence, right? Of the forecast that we have. So suppose we go short $100 worth of Meta, then we'll want to go long $500 worth of Apple. And the degree or the magnitude of the forecast and the sign would indicate how much we want to bet in a particular position. But because we're trying to, make sure that the sizing relative to other instruments in our portfolio sums up our entire portfolio, what we're going to do is, suppose we have other forecasts, right? We have 5, -1, -3, +12, 0, 5. We're going to sum up the absolute value of all of these forecasts. And this turns out to be 26. So suppose we have 26 chips in front of us, right? Oh, sorry, 16. Okay, no, it's 26. Okay, so suppose we have 26 chips in front of us to bet. This is the total amount of cash that we have in terms of the forecast, in units of the forecast. So if you bet 5 units of forecast, then we're going to take 5 over 26, and that is our portfolio weighting. And that is how we're going to, do the position sizing. So we're just going to go back to the code, and I apologize for the remainder of the voiceover. So we're in alpha score stock values. Okay, and the total number of available chips to us, so forecast chips available to us, will just be the sum of these absolute scores. Okay. Then our forecast will just be the alpha scores and the instrument. So this can be either positive or negative, indicating the direction of that. And our dollar allocation will then be the portfolio capital divided by the total number of forecast chips. If it's not equal to 0, because otherwise this will be 0 division error. And the dollar allocation and the position sizing will just be the number of this is dollar allocation per chip. So actually this is like a chip allocation in terms of dollars, and then this is the number of chips we want to bet on that position, and then this is the size of the contract, and then this will give us the overall position sizing. Right. So I think that is all for our strategy. We'll see if this runs, and we basically have 2 strategies ready. So let's see whether this works. Here Python 3.8 main.py and see if the second alpha runs as we hope. And we're implementing this from like alpha. So if this works, then we'll just go ahead and implement one more. Then we will run into a topic called parent-child relationships and object inheritance in object-oriented programming. So this will allow us to write the code in a much neater way, and we will see that as we go along. Okay, so luckily for us, the strategy was profitable. Before we go into the next lecture, just wanted to talk about the accuracy of the backtest. We are ignoring a lot of things about the practical the practicality of our backtest. For instance, we just did not really pay attention to the trading costs. In practice, you would have things like positional inertia. You would also have a lot more friction when you trade, and there's also look ahead bias and things like that. We're going to address these things later in the future. So for now, we're going to make quite a bit of mistakes, but we're just going to improve that significantly in the future. So we're just going to see you in the next lecture.